basics of logarithmic functions. Okay, we switched between logarithmic and exponential. We talked about common logs with a base of 10. We talked about exponential logs, okay, with a base of e, or natural logs. The natural log function, ln of x, is one of the basic functions introduced in section 1.3. Can you list its properties? Well, what's the domain? Okay, the domain here will be 0 to infinity. What about the range? The range goes from negative infinity to infinity. Is this continuous? Yes. Do I have to put it on its domain? Yes, you have to put it on its domain because the domain is different than negative infinity to infinity. All right. Increasing, decreasing? Always increasing, right? So we could say increasing from 0 to infinity. Are there any extrema? Any mins and maxes? No. Any symmetry? Is it symmetric to the origin or y-axis? No. This is not symmetric. Okay. Mins, maxes, continuous. Any asymptotes, I guess? We could put that in. Vertical asymptote at x equals 0. Any horizontal asymptote? No. How about limits? So we'd say the limit of ln of x as x approaches infinity would be, as x approaches infinity? It's going to be infinity. And the limit of ln of x as x approaches 0 from the right side, as x approaches 0 from the right, we'll go to negative. Now, I do not have to put on there as x approaches negative infinity because x will never approach negative infinity. Does that make sense? That limit won't exist. Yeah. It's a nice Mean Girls quote there, huh? All right. Now, as we go through this, it shouldn't be too hard to see. Now, any logarithmic function, log of x to the base b with b greater than 0, has the same domain, range, continuity, increasing behavior, lack of symmetry, and other general behavior as f of x equals ln of x. It is rare that we're really interested in log functions with a base in between 0 and 1, so a base of a fraction. So the graph and behavior of fx equals ln of x is typical of log functions. Now let's consider the graphs of the common and natural log functions that are geometric transformations. To understand the graphs of y equals log of x and y equals ln of x, we can compare each to the graph of its inverse, y equals 10 to the x and y equals e to the x. Now you should be able to see this right here, if you didn't know, is e to the x. This would be natural log. You can see that they are reflected over the line y equals x. That's the one on the left side. On the right side, this is 10 to the x, 10 to the x. And this one here is log of x to the base 10, okay, or log of x. They're reflections over the line y equals x. That's all they are. So you can tell that they are one-to-one functions. They pass both the horizontal and vertical line test. Now, previous graph, now we're going to put ln of x and log of x on the same graph to see what they have in common and shows how they differ. You can see that ln of x increases at a much steadier rate, I guess we'd say, where log of x increases really quickly, then slows down. All right. You can also see that ln of x will be less than log of x when the y values are negative, but it'll be greater than log of x once the y values go positive. All right. Now, in the next section, in the next example here, example 8, We're going to describe these logarithmic graphs. We don't have to graph them by hand in this case. On your homework, you will have to graph them by hand. Okay, there's 4 of them that you guys have to graph. Now, if we look at example 8a, what does plus 2 do? Okay, the plus 2 is going to shift it to left 2. So we're going to shift the graph of ln of x left 2. Now b, before we get into it, I'm going to rewrite it for you. That might make it a little easier for you to see. What does the plus 3 do? What does the plus 3 do? Moves it left 3. What does the negative x do? Negative x will reflect it over which axis? X-axis or y-axis? It's in with the x, so we're reflecting over the y-axis in this case. So we're going to shift ln of x left 3 and reflect over the y-axis. This one I will graph just to show you what we have, to show you that we're correct. So I'll put ln of x first, and then ln of 3 minus x second. Okay, there's ln of x. You can see that it got shifted to the left 3 and then reflected over the y-axis. What about c? What does the 3 do? Vertically or horizontally? Okay, this will be a vertical stretch by a factor of 3. And how about d? What's d going to do? It's going to shift it up 1. Because we can rewrite this. So we want to shift graph of log of x up 1. Are there any questions on example 8 at all? Good? Awesome. Now, we're going to be measuring sound here. You guys have all heard decibels and decibel level, and the higher decibel, the worse it is for your hearing. That's why you probably shouldn't be using those earbuds anymore to listen to your iPods, because it is not good at putting that sound directly onto your eardrums. But that's neither here nor there. You guys are young. You can live through anything, right? So, measuring sound using decibels. The table lists assorted sounds down here, that table. Notice that a jet takeoff is 100 trillion times as loud as a soft whisper. Because the range of audible sound intensity is so great, common logs, or powers of 10, are used to compute how loud sounds are. So this is our definition of the level of sound intensity, or decibels. So beta is going to equal 10 log of I, the intensity, divided by the initial intensity, or the threshold of human hearing. Okay? So we're going to be using this formula quite a bit here. How loud is a train inside a subway tunnel? Well, beta is equal to 10 log. What's the intensity of a train inside a subway tunnel? 10 to the negative second, right? What's the initial intensity? Well, the initial intensity is here, 10 to the negative 12. Now, can I simplify that at all? Can I move the negative 10 to the negative 12 to the top? If I move that to the top, what happens? 10 to the negative 12, move to the top, becomes 10 to the positive 12, right? So we'd have 10 to the negative second times 10 to the negative 12th, or 10 to the positive 12th, which would be 10 to the 10th power. Where are there more 10s? There's more 10s up here, right? Because negative 2 is bigger than negative 12. How many more 10s are on the top? There's 10 more 10s on the top. Does that make sense? Kind of, maybe? Okay, which we'll get into in just a bit. Now, yesterday, if you look back here, log of 10 to the y would be y, right? So going back, this here would be 10 times 10, or 100 decibels, okay? This is 10. Because log of 10 is 1, okay? That 10 comes out to the front, that's how we have 10. Why don't we see how loud a jet is at takeoff? A jet at takeoff is 10 to the third power. Simplifying this, we're going to have 10 log of what? 10 log of 10 to what power? 10 to the 15th power, which would be 10 times 15, or 150 decibels. If we look at the last one, how loud is a soft whisper? Ten to the negative 11th power over 10 to the negative 12th power, which means they'll simplify to 10 log of 10 to what power? 10 to the first power, which means I'll have 10 times 1, or 10 decibels. Are there any questions on decibels and loudness of sound and things of that nature?